I wanted to take a minute to talk about 28 again real quick. We had come up with 2 cosine t, 2 sine t, 4 cosine t sine t. And we said that this would draw the intersection of that cylinder with that weird surface. So I want to just point out that this right here is the same as 2 times 2 sine t cosine t, and that these from pre-cal, that's this right here, is this 2 sine t cosine t is sine 2t. So this is really just 2 cosine t, 2 sine t, and then this is just 2 sine 2t. Okay, so let's talk about what's happening here. We already said that in the xy plane, this draws, okay, this is x, here's y, here's z. We said in the xy plane that this draws a circle of radius 2, this does. But the z coordinate is dictated by this. So what I'd like to do is just pick a couple of points here. Let's let t be 0, see what we would get. We get cosine of 0 is 1, so that's 2. Sine of 0 is 0, so that's 0. And then sine of 0 is 0, so that's 0. So we'd be out here at 1, 2, 0. So that's where we'd be. That point lives on the cylinder, and it lives on the weird surface. And remember, the cylinder was this x squared plus y squared was 4. And then the weird surface was z equals xy. Notice that if we replace x with 2, y with 0, and z with 0, this equation is true, and this equation is true at the same time. So you can check them yourself. Now let's let t be, I'm going to say pi over 2, because that's an easy one to evaluate. So cosine of pi over 2 is going to be 0, so we get 0 here. Sine of pi over 2 is 1 times 2 is 2. And then be careful here. We're going to plug pi over 2 in here. Pi over 2 times 2 is pi. Sine of pi is negative 1, but then times 2, so we get negative 2. So we'd be 0 on the x-axis, 2 on the y-axis, and then down 2. 1, 2, like this. All right? Maybe we should take one in between there. Yeah, let's do one in between here. How about t is pi over 4? Okay, so if we do that, cosine of pi over 4 is root 2 over 2, times 2 is root 2. And then sine of pi over 4 is root 2 over 2, then times 2 is root 2 again. And then pi over 4 right here. We do 2 times pi over 4, that's pi over 2. Sine of pi over 2 is going to be 1. And then, why did I say sine? This was 0. Shit. This should have been 0. Sine of pi is 0. Okay. Sine of pi over 2, right, is 1. So times 2, so we should be at 2 here. So we should go out root 2, which is 1.41, somewhere around there. And then over 1.41, so somewhere around here. Then we should go up 2, 1, 2, so somewhere around there. So what's happening here is that we're on this circle, right? We're on this circle. Imagine this circle like this. That's a circle, and then we have this cylinder. What's happening is we're actually drawing a little sine curve, all right, part of a sine curve here on the outside of that cylinder. So it might be easier for me to show this to you with a picture. Yeah, give me a second. really hard to see this on a picture, so I'm trying to make a cylinder here. So here's our cylinder, all right? So let's imagine that the x-axis comes popping out of here. So I'm going to label that x. And then the y-axis, let's say, would be popping out over here. Okay, so what's happening is that in this first little, from here to here, right, what's happening is we're drawing the first little arc of a sine, like this. And then the backside, now look, here's the x-axis. If it punches through the backside, it would be here. And it's going to draw over here the bottom part of the sine. And then when we come around, the z-axis is going to come out here. It's going to draw top part and then another bottom part. So remember that when you put 2t in here, this is going to make your period, right? The period of a sine or cosine function is 2 pi divided by this number in front, which is just pi. The period of these two is 2 pi. So what happens is we go all the way around the cylinder in 2 pi, but we draw two of these in 2 pi. So our z-coordinate draws two sine curves in one rotation around the cylinder. I hope that makes sense. Sorry I messed up that point, but all right. Well, I guess you could do this too. Imagine this. Your z-coordinate, you take this part. There you go. There was the x-axis, y-axis, the x-axis out the other side, the y-axis out the other side, and the z. So you can see here two sine curves, right, wrapped around the cylinder. That's what that is. All right. So where were we? 39. Might be able to just do a few of these to get you going here. 39, find the derivative. Yeah, these are probably going to be pretty straightforward. So for 39, r of t equals, this is just going to be whether or not you remember how to take derivatives. T sine t, t squared, t cosine 2t. Okay, so the derivative of this vector function is going to be the derivative of each component separately. So here we have a product rule. So sine t plus t cosine t. That's what you get when you take product rule there. Derivative of t squared is 2t. Another product rule here, it'll be cosine 2t minus 2t sine 2t. So I'm not going to go through the work, but, well, I'll just show it to you. Derivative of this one is 1 times this here, plus the derivative of cosine of something is negative sine. So you get negative sine 2t, but then times the derivative of what's inside, which is 2, then times the first function, which is t, and then when you put these together, you get this. So there's your derivative. 40, 41, 42, I'll do 42, I guess. Vector function. Now they give you the IJK form, so I'm going to convert this. A t cosine 3t, b sine cube t, and finally c cosine cube t. All right, so A, B, and C here are constants. We don't know what they are. So just treat them like constants when you take the derivative. So just come along for the ride. A, and then now let's do product rule here. So, well, you know what, I'll treat these together. So what's the derivative of that? It's A times this one, cosine 3t, plus the derivative of this one, which is negative sine of 3t times derivative of what's inside, 3 times the at. Okay, so that's the derivative of the first component. This one, b is going to come along for the ride. Derivative of sine cubed t is 3 sine squared t times cosine t. So chain rule, you have to take derivative of sine also. And the last component, I'm out of room here. C comes along for the ride. Same thing that we did before, 3 cosine squared t, but then times the derivative of cosine, which is negative sine t, and that's it. So you could clean that up, but that's your raw derivative there. So 42, checking these. Okay, looks good. I thought 44 looked interesting. So it says 44, r of t equals t times the vector A crossed with the vector B plus t times the vector C. And this is weird because they don't tell you what the vector A, what the vector B, and what the vector C is, right, at all. But we know it's a vector, right? So all we're using is properties of cross products here. So before I do anything, I'm just going to simplify what this is. So let's see, how should we expand this to? This would be T A cross B, all right, TA cross B plus TA cross TC. So what I'm doing is I'm using a property. Let me go back in the book and show you where that property is. This was cross product, so this is way back in the day. There we go. This is property 3 on page 562. So we know that A cross B plus C equals A cross B plus A cross C. That's what I'm doing here. So I'm treating this whole thing as A, and I'm crossing it with B there, then A, and then crossing it with C there. All right. Then I can use the fact that this constant can come out. So T times A cross B plus, and then this T and this T both come out, so T squared A cross C. And I believe that's all they want. Yeah, that's it. So now we just take the derivative. So the derivative of this, you just take derivative of the t part. So derivative of that is 1 times that. So A cross B plus derivative of that, which is 2t, and then A cross C. On this piece right here, just so you know, on this right here, I'm using property 2. Property 2 says if you have a constant times a vector A crossed with the vector B, that this is equal to the constant times A cross B. So when I was sitting right here, and I went from here to here, just so you're clear on this, first, let's look at this. I'm going to look at this as a constant, A cross something. So I'm going to pull the constant out, A cross T, C, like that. And now for this one, I use a property again. This right here is equal to A cross C, right? But then, okay, so this right here is this with the T on the outside like that. So I can pull that T out of the cross. And then these T's come together to give me this, just so you know. All right. All right, that's 44. So now we're working on 45. And my battery's okay. So 45, find the unit tangent vector, capital T of t, at the point in a given value. So they give you R of t equals cosine t, 3t, 2 sine 2t. And at the value, t equals 0. All right, so we have to go back and take a look at the formula for capital T of t, which is the unit tangent vector. Let me see. The formula we have, I believe, did we give you 2 of them in this section? I believe we gave you 2. No? I don't have my class notes in here. Just have the book. All right, so capital T of t equals the derivative over its magnitude. So it's a derivative function over its length. I swear there was another one in this section. I have to go back and look at my notes. I don't have them. Okay, well, for now, let's just stick with this. All right, so I need a couple of things. I need the derivative first. So let me find the derivative. Negative sine t, 3. And then here, the 2 is going to come for the ride. Derivative of sine of 2t is cosine 2t, but then times 2 again, so chain rule. This will be a 4. So there's your derivative. And now what I want to do is I want to scale it by its own length. So let me find the length of this derivative. Its magnitude, which is the square root of, and now we get to start squaring stuff. So this squared is sine squared t, plus, that's 9, plus 16 cosine squared 2t, like that. All right, so is there any way we can clean this up a little bit? Well, I think we can. Let's just take a look at the inside here. We can use some identities from pre-cal. Okay, so remember, first of all, what is cosine of 2t? And there were some equivalent formulas. If you refer to your formula sheets, these would be on, let's see, this would be on reference page 2, the double angle formulas. And what I'm going to do is I'm going to use the one where I'm allowed to change that cosine 2t into 1 minus 2 sine squared t. So that's what I have right here. I can change that if I'd like into that. Where are we on here? Lost my place. Whoa. I lost my position. And second, I'm totally lost. Find the unit tangent vector. Okay, 45. Okay, so yeah, see, I'm making this a little harder than it has to be. I'm trying to come up with a formula for this, but they're giving us the t equals 0. So all we have to do is plug 0 into both of these, and then we have this. So at 0, right? Plug in 0. Plug in 0. Let's see what we get. So what is the what is the derivative vector at 0? So sine of 0 is 0, so I get the vector 0, 3, and then cosine of 0 is 1, so I get 4. I'm going to divide that by its own length, which here sine of 0 is 0, so I get square root of 0 plus 9, and then cosine of 0 is 1, squared is 1, 16, so 9 plus 16. So that's root 25 on the bottom, which is 5. So I'm going to divide each of these by 5. 0, 3/5, 4/5. Yeah, sorry, we don't need the identities because we're not trying to find a general formula. We're trying to find the unit tangent vector at 0. So it makes the problem so much easier. Okay. Now for number 45, I think you can handle, 46, 47, 47. Let me do 47, it's a little different than 46. So for 47, they give you r of t equals t squared, t cubed. You're asked to find the following: r prime t, capital T of 1, r double prime t, and r prime t crossed with r double prime t. 4 different things. So let's first find the derivative. 1, 2t, 3t squared. All right, that's done. All right, find the tangent vector at 1. This is the derivative at 1 over the magnitude of the derivative at 1. So what happens if I plug 1 in there? I get 1, 2, 3. And then the magnitude at 1, so the magnitude of those squared when you plug in 1, so 1 squared plus 2 squared plus 3 squared, which is, let's see, 9 plus 4, 13, 14, so root 14, so 1 over root 14, 2 over root 14, 3 over root 14. Just double check these, so, yep, okay, now we've got this. What's the second derivative? Well, the second derivative, I'll just put it up here, is the derivative of this one, which is 0 to 6t. So I've got this. And now I'm going to cross the derivative with its second derivative. So I'm going to take the vector 1, 2t, 3t squared. I'm going to cross it with the vector 0 to 6t. And then I'm going to do what I've done in the past when I cross two vectors. If I want to get the I component, so if I'm going to cross these two, get the I component, I cover up I. I've got what here? This times this, that's 12t squared. Take away 6t squared, which is 6t squared. Now I cover up this one. 1 times 6t is 6t, 0 times that is 0. So I have 6t, but then I subtract it, so minus 6t. And I cover up this one. 2 take away 0, it's just 2. All right. That's all I wanted. Okay. So you should be able to do number 48. It's very similar to that one, except they ask you for some different stuff. All right, 49. Find the parametric equations for the tangent line to the curve at with the given parametric equation at the specified point. Okay. So I'll do one of these. So 49. They give you a vector function, has parametric equations, 1 plus root 2t, come on, root 2t. The y component is t cubed minus t. The z component is t cubed plus t. And we're looking at the point 3, 0, 2. Okay, so imagine that if you were to draw this, this is a curve in three-dimensional space, right? Whatever it's doing, doesn't matter, it's three-dimensional. And at a certain point on that curve, exactly the point 3, 0, 2, right? There's some direction, like when you draw this, there's a direction that the curve's being drawn in. Then there's some tangent vector here, and that tangent vector creates a line, right? So I'm trying to find the parametric equation for the line, this line right here, the parametric equations. So a couple of things. What do we need for a line? What do we need for the equation of a line, the vector equation of a line? Well, we need a point and we need a direction. In fact, we always call that direction vector v. The point would give us the r naught. So that's what I need. This is what I need for the vector equation of a line. This is back in the previous section. All right, so the question right now is, do we have a point? Well, yeah, of course we do. We have this point, 3, 0, 2. So I've got this taken care of. What I need is a direction vector. So the direction vector is this vector here, the blue one. But that blue one is actually the derivative of this vector function at some point in time, right? At a specific point in time, which I don't know right now. They didn't give me the point in time. But I should be able to figure out what that point in time is by looking at the point. So what t would I plug in here to get 3, 0, 2? So, 302, is that the point? Oh, you know what, I wrote this backwards. This is this, that makes things a lot easier, okay. It was 2 root t. Yeah, I'm making lots of mistakes today. So I think it's obvious if t is 1, that this will work. I'll get this point, so if that's 1, this is 2 plus 1, that's 3. If that's 1, I get 0. If that's 1, I get 2. So this is it, t is 1. So what I really want to know is what's the derivative here at 1? Right? That's what I want. So I first need the derivative. The derivative at 1, right, is equal to my direction vector of my line. So let me get my derivative first. The derivative of this is, let's see, derivative 1 is 0, derivative of this, cover the 2. So derivative of square root t is 1 over 2 root t, then times 2. So this is 1 over root t. And then derivative of this is 3t squared minus 1. Derivative of this is 3t squared plus 1. And now let's plug 1 in. So what's the derivative at 1? That would be, let's see, 1. This will be 3 minus 1 is 2. And then 3 plus 1 is 4. So this should be the vector 1, 2, 4. So I'm ready to come up with the vector equation of my line using these two things. Now I am going to do something a little different. We in the past have used r of t, but r has already been used. So I'm going to call it s of t. S of t is going to be r naught, which is the point written as a vector, plus t times v. and v is my direction vector 1, 2, 4. Which means that S of t is, put these components together, 3 plus t, 0 plus 2t, so 2t, and 2 plus 4t. And that's the vector equation of this blue line right here. It'll draw this blue line. Now, they want it in parametric form, so x is 3 plus t, y is 2t, z is 2 plus 4t. And let me just double check that. 3 plus t, 2t, 2 plus 4t. Yep, that's it. Okay, so number 50, 51, and 52 are done the same way. The functions are a little more complicated. 53. Find the vector equation of the tangent line to the curve of intersection of the cylinder, blah, 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 and blah, blah, blah at the point. All right, that 53 is a good problem. It took me a second reading it to understand what they wanted. So for 53, we want to, well, I was supposed to be doing odds here. Whatever. Stop paying attention to that. Find a vector equation of a tangent line to the curve of intersection of these cylinders. So you have two cylinders. That one and then they give you a point. All right, so we have two cylinders. This is a cylinder that has a radius of 5, and it opens up the z-axis like this. It goes up the z, right? And then this one, the x is free, so it's going to come out the x-axis. It has a radius of root 20, whatever that is. So it's smaller than this one. So it's like coming out the x-axis, going in, hitting here, popping out the other side like that. So where these two curves intersect each other, right, there should be some intersection of these two, and on the back side there's some intersection also. I can draw these red things with a vector equation. So I need to come up with the vector equation that draws that. Then, once I've done that, I need to go to this point, 3, 4, 2, which is on that curve of intersection, and I need to find the tangent line to the red curve. So it's the same as the previous problem, that we have to find the line that's tangent to a curve, except they didn't give us the curve right off the bat. We have to find the curve ourselves. So we're trying to figure out where these two intersect each other. So here's what I'm going to do. I'm going to start with the first cylinder. I'm going to draw that with a vector equation. I'm going to call it C1 of t. All right, cylinder 1 of t. And that has, how do I draw a circle radius 5? So 5 cosine t, 5 sine t, right? And the z is free. However, this equation gives us a restriction on z. This tells us that z squared must be equal to 20 minus y squared, which means z must be plus or minus square root 20 minus y squared. And I'm going to only look at the positive, and the reason why is because there's two curves here, right? The front one and the back one. If I'm going to be looking at the point 3, 4, 2, my z-coordinate is positive, which means I need this to be the positive case. So I'm just going to look at that right there. Okay, so my z-coordinate right here must satisfy this equation. So it must satisfy that root 20 minus y squared. But y, remember, is this. So square that, you get 25 sine squared t. That is the vector equation. Sorry, I should just call this, because this is not the vector equation of this cylinder, it's their intersection. So why don't we just call it, I don't want to call it R, intersection, crossing, however you want. I'll just call it S of t, all right? And then I'll let this one be the R. All right, so there it is. Now I'm going to verify my work so far before I start taking derivatives. Yeah, that's it. So at this point, I need to know what the derivative of this is. So you know what? This is R. I'm getting upset with myself for switching so many of my things today. Just, it's a Monday for sure. Look, I'm looking for the red. This is it. I call it R. Look, this by itself would draw this cylinder, but once I restrict that Z coordinate, then it draws the intersection, which is what I'm calling R. So I need the derivative now, right? Because remember, I'm trying to find this green line that goes forever in each direction. I need a point. I need a direction vector. I have a point, here it is. I need a direction vector. The direction vector should be the derivative of this right here at some point in time. I'm going to have to go figure out what that point in time is here in just a second. So what do we got derivative-wise? So take derivative here, you get negative 5 sine t. And then take derivative there, you get 5 cosine t. And then this derivative actually sucks pretty bad. Chain rule, so 1 over 2 roots of all this times the derivative what's inside. So derivative 20 is gone. Derivative of this, the 2 comes out, so negative 50 sine t times derivative of sine, which is cosine t. That should be it. My phone is going crazy. All right. Now, how do you find t? That's going to be tricky, right? So all I need to know now to get my direction vector is to figure out what point in time gives me the point 3, 4, 2. All right, that's not obvious, is it? So let me see if I can convince you of what it is. Okay, what I know first is that this right here, right? This right here has to turn into a 3. This one has to turn into a 4. And that one down there has to turn into a 2. So let me just first try and make 5 cosine t turn into 3. Well, that's cosine t is 3/5. And then I can get on my calculator and I can figure out what arc cosine of 3/5 is. Right? Figure out what that is. Then I also need that 5 sine t equals 4. Which means that sine of t must be 4/5. And I can go on and figure that out. But if you notice, we've got a 3, a 4, a 5. This looks like a right triangle, a 3, 4, 5 triangle. 3, 4, 5. Here's t. Let's see if this works. Sine of t here would be opposite over hypotenuse. That's this. Cosine of t would be adjacent over hypotenuse. That's 3/5. So this looks like the correct triangle, doesn't it? So these t's should be the same. And then the last one, well, how in the world do you figure this out? Well, that's going to be much harder. How do you determine that that's 2? Well, we don't. We know that we're just going to trust that this angle, t, is going to work for all of them. You could check it. Get on your calculator, figure out what this is, okay? And then plug that in right here, and you should get 2. All right, so once you have t now, once you have t, you can go and you can get the value of the derivative at that t. So watch how I'm going to do this. This is going to be very clever. What is the derivative of the function at the t, which is this value, which I'm going to say I don't know what it is. Well, it's negative 5 sine t. Well, what was sine t? 4/5. So what's negative 5 times that? What's negative 5 times 4/5? Negative 4. Okay, 5 cosine t. What was cosine t? 3/5. So what's 5 times 3/5? Well, that's just 3. This one might be a little bit harder. What's sine squared t? So what's this squared? That's 16/25. Okay, multiply it by 25. And what do you get? 16. What's 20 minus 16? 4. What's the square root of 4? That's 2. What's 2 times 2? That's 4. So this is just 1/4 times, over here, sine t times cosine t. That's 4/5 times cosine t, which is 3/5 times negative 50. So what? This is 25, goes into 50 twice. And then, so this is going to reduce out to be a 2. So we have negative 2 times 4 times 3. That's 24, so negative 24. And that's just negative 6. So this is the vector negative 4, 3, negative 6. Going to check it. Yes. All right, so now I'm ready for the equation of the line. This is nuts. So the equation of my line, which I'm calling RT, was the point turned into a vector, 3, 4, 2, plus t times my direction vector, which was negative 4, 3, negative 6. And I think we've done this enough. Put those together, you're good. All right, 55. Should be able to do 55. 57. Let me give you a hint on 57. You have two curves. They give you two curves, R1 and R2. They tell you they intersect at the origin. So you got some curve, you don't even know what it's doing, R1. You got some other curve, you have no idea what it's doing, R2. But you know they hit at the origin, right? So what you're trying to find is their angle of intersection. So what you're going to do is you're going to find the tangent vector, right? So R2 prime, right there would be this blue one. And I don't have any other good colors, but let's just say R1 right here. You're going to find the tangent vector coming off of this R1 prime, right? Those two vectors, right? You can get those just by taking the derivatives at the point 0, 0, 0. Once you find those two vectors, you just have to find the angle between them. And remember how to find the angle between two vectors. Cosine inverse, dots, divided by magnitudes. Go back and look in your notes. You should be able to get the angle. So that's 57. All right, 59 through 63. So evaluating an integral. Let me do 59. And I'll let you do the others. So 59, you have, what is the integral from 0 to 2 of the vector function, and I'm going to rewrite it in vector form, t negative t cubed 3t to the 5th dt. So we're integrating a vector function. So integration of a vector function is fairly easy. We just integrate term by term. So this is 1/2 t squared. This one is minus 1/4 t to the 4th. This one is going to be 3 times 1/6 t to the 6th. So the 3/6 reduces, plus some constant vector. And that constant vector we're going to rewrite that constant vector like this. C1, C2, C3, like that, right? But because this is a definite integral from 0 to 2, this constant doesn't matter, right? So with definite integrals, you don't have to worry about this constant. All right, if it wasn't a definite integral, then you would have to put this in here, and you would just add, you know, be this plus C1, this plus C2, this plus C3. So because it's definite, I don't need to worry. So all I need to do is evaluate this at these two. So first, let's plug in. Let's plug in 2. What happens if we plug in 2 here? 4, half of 4 is 2. Plug in 2 here. What do we get? 16 divided by 4 is negative 4. And then plug in 2 here. What's that? 16. 32, 64 divided by 232. Then we plug in 0, everything's 0, so the 0 vector. So it should just be this one right here. Let's see if I did that okay. 2, negative 4, 32. All right, and then you can do 61 and 63 yourself. All right, that's it for this section. Sorry, I was kind of all over the place this morning, a little scattery. It was a good weekend, I guess.